Okay. Good morning. My name is Jerod Rasmussen, and today I'll be giving a short talk focused on a novel approach for characterizing white matter development in the time period centered around 39 weeks post-conception. Because this is a developmental conference, I don't think you need convincing of the motivation for this work, but it does bear repeating. The motivation is knowing what normal development looks like in order to more accurately define abnormal development. In turn, this helps describe what outcomes of abnormal development are, as well as what leads to abnormal development to begin with. Now, we all know that brain growth is incredibly rapid during early life, but what I'd really like to impress upon you is just how complicated it is. Not only is it temporally overlapping, it is spatially asynchronous. As an example, the projection fibers running between the precentral gyrus and the thalamus contain regions that are considered peripheral and show signs of myelination near 51 weeks post-conception, whereas regions that are more central anterior show myelination much earlier at 38 weeks post-conception. Because true myelination requires a preceding stage of oligodendrocyte proliferation, then true myelination begins near to or after birth, we have our first testable hypothesis. Birth is roughly straddled by a pre-myelinating stage of oligodendrocyte proliferation and a true myelination stage where layering of myelin sheathing occurs. Now, I want to be careful in saying that this is not an original or controversial hypothesis, but simply a developmental characteristic we'd expect to observe using our proposed method. Before I go into more specifics about the ontology of white matter microstructure, I'd like to cover some basic terms used in this talk. For those that aren't familiar with diffusion tensor imaging, DTI is a method of mapping the fiber tracks connecting relatively distant regions of the brain. The strength of these connections is frequently referred to as structural connectivity. On the left-hand side here is a cartoon depicting a fiber tract ensheathed in a lipid bilayer of myelin. This reduces the permeability of water into and out of the axon, limiting diffusion perpendicular to the axis. Of course, this is the whole point of myelin, increasing the efficiency and speed of the saltatory conduction. On the right-hand side, we have some defined values: axial diffusivity, AD, or the amount of diffusion along the axis; radial diffusivity, amount perpendicular to the axis; and fractional anisotropy, a measure of how anisotropic the diffusion is. So a high FA would correspond to an elongated ellipsoid as seen on the left. In this example, mature myelin is in place. In earlier stages, myelin is not present and there is little restriction on diffusion, resulting in a more spherical shape. When myelin-producing oligodendrocytes begin to proliferate, there's an isotropic reduction in diffusion, decreasing RD and AD more or less equally. When the oligodendrocytes begin to produce true myelin, this is manifested as an RD reduction, resulting in an increased fractional anisotropy. This concept is reiterated in the following image. Highlighted here with the red box is the time period of greatest relevance to today's discussion. As you can see, during oligodendrocyte proliferation, water is increasingly restricted in all directions, resulting in a greater reduction in RD, while FA is relatively unchanging. Following this pre-myelination stage, the oligodendrocytes proceed to lay down myelin, resulting in a continued decrease in RD, but not AD, and a resultant increase in FA. Now, these processes are temporally overlapping, but it is thought that because oligodendrocytes are required for the creation of myelin, changes in FA are preceded by changes in RD and AD during this stage. Some of the pioneering work and inspiration for this talk today can be seen here. By taking advantage of the expected precession of RD and AD, changes followed by FA, the authors were able to nicely demonstrate maturation asynchrony. However, this method requires an adult sample using the same scanner and sequence, as well as gives only a sumarial measure across an entire tract. Finally, one can also see here that this model fails for a few major tracts, including corpus callosum and the uncinate fasciculus as seen by regions colored gray. That leads us nicely into the task at hand, which aims to do a similar but tract-based analysis without collecting an adult sample. To do this may seem counterintuitive in that it requires making inferences about developmental trajectories from a cross-sectional sample. However, as you will see, because these infants have normally distributed gestational ages and postnatal ages that are completely independent of one another, and with nearly equal variance, we can do so. In this work, we define PC as post-conceptional age, GA is gestational age at birth, and SA the postnatal age at scan. As you can see on the bottom panels, there are three different ways to arrive at the same endpoint: prenatal growth, linear growth, or postnatal growth. Now, consider the case of purely prenatal growth as seen again here on the top left. If this type of growth is present in, say, a number of individuals with normally distributed gestational ages at birth, we arrive at varied levels of development at the time of scan. which are entirely dependent on gestational age of birth, as seen in the bottom left panel. In contrast, the case of purely postnatal growth is shown on the right, linear growth is shown in the middle. There are two important features here. One, by breaking up the independent variable PC into two independent variables GA and SA, one is able to more appropriately account for the variance and accurately model the behavior. And two, if one were to model its development with a single variable PC, as is commonly done, the conclusion would be misguided in the cases of asymmetric development, and an inaccurate residual variance would remain. In the case of symmetric or linear development, PC would be an appropriate variable, but one can see that splitting up PC into GA and SA does not sacrifice any explanatory power, as 100% of the variance is still accounted for by GA and SA in combination. By breaking up post-conceptional age into gestational and postnatal age, we're best equipped to consider differences in pre- versus postnatal contribution to development. In order to characterize the relative contribution of pre- and postnatal time periods, we conceived of a simple and unitless index, termed the maturational index, that captured whether development was weighted towards either the gestational period, the postnatal period, or both equally. This index is defined as the difference in the explained variance between gestational age and skin age divided by their sum, and is similar in concept to the laterality index used in fMRI. The model is best explained by the gestational period, it tends towards +1, and if best explained by the postnatal period, it will tend towards -1. The linear trajectory would be characterized by null value, as GA and SA are equally explanatory, reducing the numerator to 0. This is a generalizable index that will apply to any variable. However, inferring a maturational state requires a sigmoidal developmental trajectory active during your age variables. In the case shown here, the simplest interpretation of the MI is a more positive value suggests a less mature state, whereas a more negative value a more mature state. Of course, when the variance explained by both variables is very low, the MI can be unstable as seen by the endpoints in this graph. These data points are determined by non-significant associations with gestational age and scan age, and are masked in the remaining analysis shown today. Perhaps this model is best summed up as the acceleration of a developmental trajectory. As you can see, MI describes a relative quickening or slowing of the linear approximation of trajectory around the time of birth, so that is the method we'll now consider in application. In the interest of time, I'll cover the basics of the study quite quickly. 47 participants, ranging from roughly 36 weeks to 41 weeks gestation, were recruited during pregnancy and imaged on a 3 Tesla semen scanner. The imaging protocol also includes a battery of structural scans, although I have summarized the diffusion-weighted protocol only here. The pre-processing pipeline consists of a strict QC process, followed by atlas building, tractography on the atlas, individual registration to the atlas, and finally, extraction of the DTI metrics from the group-defined tracks. When building a hypothesis, it's important to consider that pre-myelination and true myelination are the dominant mechanisms of white matter development at the time of birth. In this cartoon, pre-myelination is depicted on the top, with the bulk of development occurring before birth and limited to changes in RD and AD values. True myelination, on the other hand, is shown on the bottom, with FA and RD development primarily occurring after birth. Within this framework, one can see that the expectation value for MI of FA is a negative value, whereas a positive MI value is expected for AD. RD, on the other hand, decreases for both processes and should therefore take a value between MI of FA and MI of RD. This forms our second hypothesis, in order from negative to positive, MI of FA, RD, and AD. The plot seen here is a cumulative distribution function of MI across all white matter data sampled for each of the 3 metrics of diffusion. As expected, RD and AD have significantly higher MI than FA, reflective of the pre-myelination stage preceding true myelination. In addition to the average values, one can see that roughly 70% of the data show positive MI of AD, 70% negative MI of FA, while RD is centered around 0 with a Gaussian distribution. Recall this observation is due to early changes in RD and AD trajectory during pre-myelination, followed by an increase in FA and a continued increase in RD due to true myelination. The proposed temporal sequence is highly significant in this cohort and supportive of our first hypothesis that pre-myelination precedes birth while true myelination succeeds birth. I'd now like to revisit our cartoon and consider cases where changes in one process are dominant, either pre-myelination or true myelination. Circled in red are expected observations of pre-myelination, a positive MI of RD and AD. Circled in blue are expected observations of true myelination, the negative MI of FA and RD. As an example of this, we can focus on the thalamocortical tract highlighted earlier, specifically from the premotor cortical region to the thalamus. Based on post-mortem studies, we might expect the more peripheral region to be dominated by an earlier stage of development, namely late-stage premyelination. Conversely, based on observable myelin at birth in the more central regions, we would expect a later stage of development to dominate, namely early-stage true myelination. This figure is a detailed breakdown of the statistics along the premotor corticothalamic tract. In the top row, we can see a rough bisectioning along the profile separating the central and peripheral regions indicated by a dashed vertical line. The middle row is the maturation index along the tract and shows an even more consistent separation between the central and peripheral regions. The dashed colored circles highlight the most relevant feature of this plot. The central region is characterized by significant MI of RD and FA, while the peripheral region is characterized by significant MI and RD and AD. This is further evidenced in the bottom row by the beta values for rates of change, where one sees a flip between the growth rate before birth and after birth, indicated by dashed and solid lines respectively. These next figures extrapolate the data out using percent change relative to the average time of birth, roughly 39 weeks, to better illustrate the dynamics at play. In the case of the central region, the relative quickening of FA and RD suggests a ramping up of true myelination, whereas the stalling of AD and RD in the peripheral region suggests a slowing of premyelination. Again, this is consistent with the relative maturity expected in the inferior corticothalamic tract located near the internal capsule, which has been identified as one of the earliest maturing white matter regions by a post-mortem and myelin water fraction MRI. Conversely, one of the central tenets of white matter development is that peripheral portions of a tract tend to develop after regions more central and supported by the dynamics shown here. Back to our cartoon. I'd like to point out that the sign of RD alone can be descriptive of the dominant type of process occurring. A negative RD accompanies premyelination dominant processes, whereas a positive RD would be indicative of true myelination dominant processes. When one process dominates, the sign of the maturation index for RD is skewed. In other words, one would expect negative MI of RD to be associated with the MI of FA and true myelination, whereas premyelination dominant processes would be indicated by a positive MI of RD associated with MI of AD. This is confirmed in the following plot. Here we've expressed this in absolute value of MI of AD or FA versus RD. As predicted, negative values of RD are most associated with changes in MI of FA and likely reflective of true myelination dominant changes. Positive MI of RD, on the other hand, is likely reflective of premyelination dominant changes in MI of AD. Finally, here we have whole brain mapping of maturation index for RD. Immediately, a couple of things are apparent. The different class of fibers can be seen to have a high degree of asynchrony from each other. For example, the commissural fibers are roughly characterized by positive to null MI of RD. Associated and limbic fibers have a range of positive and negative MI, but lower in magnitude. And projection fibers are bisected by regions of large positive MI and large negative MI. 2, in many cases, a sumarial measure over an entire tract poorly characterizes the true nature of the maturation process involved. For example, the majority of the fibers show regions centrally suggestive of true myelination dominant processes, with peripheral regions more dominated by what appears to be premyelination. In summary, we've demonstrated the logic behind the maturation index and shown the ability to reflect changes in microstructure reflective of complex biological processes. This includes evidence pertaining to the sequence of events related to oligodendrocyte proliferation and true myelination and the time of transition between these two stages roughly occurring around the average gestational age of birth. Because this technique is highly generalizable, we'd like to apply it to an array of developmental phenomena measured with MRI, including structural features like cortical thickness and gyrification, as well as measures of functional connectivity and network properties. We also have hope that splitting up into treatment groups and examining differences in MI can yield insight into relative delays in maturation. Some notable caveats. Development is assumed to be linear, as this is driven by a linear model during the pre- and postnatal time periods. Additionally, this method is really looking for nonlinearities about the time of birth and therefore cannot separate what may appear to be changes in trajectory from changes due to drastic differences in environment, for example, the influx of afferent signaling following birth. I'd like to thank, in particular, the amazing staff responsible for acquiring these data. For any of you that do or have tried to do neonatal imaging, you know just how trying this can be at times. I'm supported by a wonderful cohort of advisors, including Claudia Buss at Charité and Patrick Wadwa and Fritjof Krugel at UCI, and this work certainly would not be possible without them. Finally, the folks at UNC who have contributed immensely with their fantastic QC and pre-processing expertise on display today. Thank you.